I already told you that this has to be a Hilbert space. This has to be a linear category. So now we are already slightly scared what kind of beast lives here. So technically it should be a linear 2 category, but we have something called the Morita approach. So let me tell you something about targets. So targets for functorial field theories. So if we were pure algebraists, our life would have been simple because we have the category of vector spaces and linear maps. And now I want to have a category of 2 vector spaces, which is a bicategory. So it has objects, 1 morphisms, 2 morphisms. And the general rule is that this 2 category will be a symmetric monoidal 2 category, meaning I can multiply or make sense of taking 2 objects together as a tensor. And there is a special object called the monoidal unit in this 2 category. Whenever I take the endomorphisms of the monoidal unit in, let's say, n plus 1 vect, I should get n vect. So whatever this 2 category will be, whenever I go to the monoidal unit of that category and I look at the endomorphisms, it should give me vect as a category. And it turns out there are 2 very nice models for this, at least in the bicategory case, which is the Morita category of algebras or the bicategory lincat. So the Morita category of algebras has objects algebras, 1 morphisms bimodules of algebras, and 2 morphisms as equivariant maps of bimodules. And the composition of 1 morphisms is given by tensoring over that algebra. So I'll just write an instance of what it looks like. So this will give me composition, and then I can have maps AB to M2 AB. I'm sorry.
Yeah, I have a question. So in conformal field theory, sometimes people think that there is a kind of there is an isomorphism between a circle and a point. No, it's like the state of PE correspondence. No, so I would say that in a circle I can put I don't know some. In a point I can put the same basically.
Yeah. So the idea is that this point is not the point that you get by limiting the circle down to 0. This point is what you get when you chop up your Riemann surface in 2 different corners. So this point is the gluing point. Like this point is actually a point on, suppose I give you a sphere and I basically want to evaluate spacetimes that look like this. So this point that I'm talking about is a point that is actually a thing that can be glued on, whereas the point that you'll get after limiting this circle will be actually a point insertion, and they are notionally different things. But when I say extend down to the point, I mean if you give me a spacetime, if you give me a torus, I can cut it in many places and I can cut it into pieces that have corners. Usually when you are doing this assignment, you only cut such that your boundaries are circles, but I'm saying you can cut it even further.
So it's like boundaries.
It is like boundary.
It's corner, yeah.
Yeah. Okay. So for my vector spaces as targets, I have these 2 models for bicategories that can be used in the place of 2 vect. So I have the Morita category of algebras, as I said, algebras, bimodules, equivariant maps, and I have lincat as a bicategory. Categories, linear functors, natural transformations, and if I put nice enough adjectives, I can get an equivalence where the functor downwards is just take the representation category. So I take an algebra, I take its representation category, I get a linear category. Now, luckily, 3 vect is also something that people have already studied. and I'll do exactly what I did here, which is morally just look for algebra objects in your category that you already had. So what I'll do is just I look for algebra objects, things that have some sort of associative algebra structure in this category. And what I'll get is the Morita category of tensor categories. And this is a 3 category. So the general approach is look for algebra objects in your previous category and take the Morita of that. And this would be Lin 2 cat, but people don't use this because this gets ugly, whereas Morita category of tensor categories is nice and well behaved. But my interest lies not in vect, but in Hilb, because it's crucial that these things have some sort of inner product structure. So now if I want to do the same thing with Hilb, the category of Hilbert spaces and bounded linear maps, can I try to give you models for 2 Hilb? Firstly, if I try to do the same process of looking at associative algebra objects inside Hilbert spaces, I get very nasty things. So this machinery breaks, but lucky for us, we already know what we want here. We want the Morita category of von Neumann algebras. So this is von Neumann algebras, let's say R, then von Neumann algebra modules, R1, R2, and the composition is now given by cons fusion instead of just the tensor product of bimodules. So R2, R3, cons fusion. Just to point out, the identity 1 morphism is the algebra itself, whereas the identity 1 morphism in this case will be L2 of R. So identity is L2. And then again, equivariant linear maps. So this forms a nice category. People have studied this category before, nice bi category. And again, you can ask me, what does this model correspond to in the Hilbert space setting? And it turns out it corresponds to what I call W star cat, which was again first studied in the 80s. And we recently wrote about this. So W star cat is again a bi-category, very similar to Lin cat, which is again, you have the functor here rep, which gives you an equivalence of categories. So objects are complete W star categories. So W star categories are, let me give you a definition. So it's a W is, well, fancy W is a W star category if this definition is sounding so tautological. I'll say W is a W star category if it is a star category. So star already has meaning hidden inside. So it is dagger and C linear. If anybody does not know what some of these terms mean, please stop me at any point. Such that endomorphisms of each object in this category is a von Neumann algebra. This is the easiest way to state it. If I assume that my category has finite direct sums, otherwise I would have had to tell you what is the structure on the Hom sets, which I don't want to. So I'll just tell you what is the structure on the endomorphisms of each object, and you can always take a direct sum of 2 objects, look at its endomorphisms, and project down to the Hom sets to find out what is the structure there. Okay. So W star cat object has our complete W star categories. One morphisms are what are called W star functors, and two morphisms again. I'll just say W star or just star natural transformations. Okay, so what I want to stress is that these behave a lot like Hilbert spaces. In principle, you can try, they firstly admit an inner product, and that inner product satisfies something which is very similar to your Reese's representation theorem. So they genuinely are like categorified Hilbert spaces. So I should probably at this point give you an archive reference because we made a big table for why they look like categorified Hilbert spaces. So archive 2411 8 version 1. So this is joint work with Andre and Dave Pennies, where we discuss this category, W star cat, and show why it looks like categorified Hilbert spaces. Again, we should remember that why we were interested in Hilbert spaces and not vector spaces was because of this dagger structure we have on linear maps, the adjoint of a linear map. And it turns out that these bi-category is appropriately fully dagger. So it has involutions at the level of objects and one morphisms and two morphisms. So this is fully dagger, just like Hilb as a category was a dagger category, in the sense that you could have taken adjoints of linear maps. Okay, so I have now told you what kind of object lives here, but again, that was not what I wanted. I wanted to go at the level of 3-vect, which is essentially what I will try to tell you now. So 3-Hilb. What did I end up doing here? I ended up taking a categorification of algebras as tensor categories. So algebras are like algebra objects in vector spaces, and tensor categories are like algebra objects inside linear categories. So I want to do something similar. I want to categorify von Neumann algebras, just like tensor categories categorified algebras. And von Neumann algebras are rich function analytic things. So I'll call them bicommutant categories. So the name bicommutant categories comes from the famous bicommutant theorem that von Neumann algebras satisfy. So von Neumann algebras are closed under all the nice topologies that you can put on operator algebras. But there's a very nice characterization which is purely algebraic, and that is what we try to categorify because that is because we don't know how to categorify topologies so far. So I'll give you a little table of analogies, basically, which will tell you how these categorify von Neumann algebras. So von Neumann algebras and bicommutant category. So it's an algebra which is C-linear, and this will be a C-linear tensor category. So that is the underlying structure that we already expected. In principle, this is an algebra, and in principle, this is a C-linear tensor category. Now, there is star structure. And that translates to what I call pulley dagger structure. So I have involutions dagger 0 and dagger 1 on objects and morphisms. So the example I want you to think of is just Hill, the category of Hilbert spaces. The dagger 0, which I say is an involution on the level of objects, is giving you the complex conjugate of that Hilbert space. And this is what dagger 0 wants to do. And dagger 1 wants to take F from H1 to H2 to F dagger from H2 to H1. So these are two involutions that are present on the category of Hilbert spaces. And I'm claiming a general C-linear tensor category which has these two involutions is equivalent to saying this algebra has a star structure. Okay, then I have to take commutant. So if A sits inside B, I can define A commutant to be B in B such that BA equals AB for all A in A. And for that, I have to now give you something which captures this. And every time we are trying to categorify, we need to remember that equalities now become structure. I have to give you data such that this thing holds. So this is also something that is already defined. So suppose I have a functor from T to E. I'm just replacing A and B by T and E, which are now categories. It's a tensor functor. I can define the relative center of with respect to this functor. So Z is my fancy Z is my notation for relative center, which is this commutant notation. Technically, I want to write P commutant, but I also want to remember what functor it corresponds to. In principle, here it was just an inclusion, but I want to remember this functor. So that's why I write Z of this functor. But technically, what I want to say is T commutant in this category. So objects of this category are pairs X comma EXY, which is this half braiding, X tensor IY to IY tensor X for all X in T. So this is data. And this is natural in Y. So that's why I call it half braiding. So X and T. Okay. And morphisms from X1, comma, E of X1. So all the half braidings to X2 and all the half braidings with respect to X2 are maps F from X1 to X2 that satisfy that basically you can slide this map across half braiding. So I'm just going to draw a picture. So suppose this was my E and F was sitting here. This is equal to if I had done F here and done this. So maybe I should put some labels. X1, Y, this was EXY. And now I have this is X1, Y, and this is X2. So F was a map between X1 and X2. And now I can first do F from X1, X2, and then do the braiding with X2, and then get Y here and X2 here. So this is just checking whether this is a good morphism or not. This is the data of the morphism. So this is relative center. with respect to a functor. And now I can easily write what I would want the bicommutant property to look like. So here what we write is A equals A double commutant, or what I want you to think of is that A comes equipped with this canonical Hilbert space, L2A, which has left and right actions of A on both sides. So I can either say A equals A double commutant in some arbitrary representation that I choose, or I can use this canonical Hilbert space, which is a bimodule over A, and say left and right actions are each other's commutants. Actions are commutants. So this is what I'll try to impose here. So first I have to convince you of what is the correct thing to take in place of L2A for my arbitrary tensor category, which comes equipped with some involutions. So the correct thing to take here is what I'll call the abs. So this is T was a tensor category, and there is an ideal inside this of absorbing objects. So omega is absorbing if omega tensor x is isomorphic to x tensor omega for all x. So I take the ideal of absorbing objects. So in my Hilb example, the infinite dimensional Hilbert space is the absorbing object. And absorbing object is always unique up to isomorphism, but not unique isomorphism. So what I want you to think of this absorbing objects is something like selecting the Hilbert-Schmidt operators of some kind, or basically selecting an ideal which is nice. And this will admit actions of T on left and right just by multiplication by an object in T. So I can always take an object in T and tensor it with an absorbing object. I still land here, which gives me left and right actions. And now I can just impose this same condition here. Left and right actions are commutants of each other. And this is basically the structure of the definition of a bicommutant category. I've literally went step by step through the definition of a one-Neumann algebra and done my best to categorify it. There's lots of maps that are data in this definition, which satisfy a lot of coherences, which I'm not going to tell you. But let's for now assume that you believe me that this is the categorification of a one-Neumann algebra. So now, first thing, now I define my construction. So what am I supposed to do? I'm supposed to take a conformal net and produce a category which will be a 3 Hilbert space in this sense, and I want to assign it to the point. So construction, input, a conformal net. I was thinking of writing the definition of a conformal net, but I won't because I realize I don't have enough time. But the data of a conformal net is you have a circle S1. It comes with a canonically given Hilbert space, which I'll call the vacuum sector. To every interval of this circle, let's say I assign a one-Neumann algebra A of I, such that this satisfies the conditions that we have seen a lot of times this morning, which is isotony. So if my interval lies in a bigger interval, then that gives me an inclusion of the algebras. If the two intervals are separated, they have disjoint like they do not intersect, then their algebras commute inside the bounded linear operators of this. There's a projective representation of diffeomorphisms on this Hilbert space of S1, and it is covariant with respect to this action. So I'm not going to write out what the definition of a net is, but for all purposes, you need to remember that you have an algebra assigned to every interval on the circle, which behaves well. And just to connect it with the Hardcastle axioms, the way it comes, the way you get this is by taking a Minkowskian cylinder and basically projecting or selecting only the chiral part of the observables, or only the right moving observables, if you will. And that's how you get this circle. So each interval on this circle actually represents a ribbon of right moving parts of observables on this cylinder. Okay, so I make a category which I'll call sol of S1, comma P of A. Let's call my conformal net A. So sol has objects Hilbert space H with actions alpha j of AJ to B of H. For all intervals J S1 such that this point P, which I choose on my circle, does not lie in the interior of J. So I want the action of all intervals that don't contain the point P in their interior, and morphisms are maps of H1 and H2, which respect the actions.
Excuse me.
Yes.
Are you assuming there's a vacuum vector at all in your?
Yes, the data of a conformal net also comes with a vacuum vector, and yes.
This invariance.
Yes, that is invariant. Yeah, I just did not give you the full definition of the conformal net.
The
Okay.
Sol is soliton.
Huh?
Sol comes from soliton.
Sol comes from soliton. Yes. Though I do not understand the why people call it solitons, but okay.
Either.
I will. So this is a category. This is a tensor category. This is tensor. It has these dagger structures that I want, but it also has an equivalent description. Let me go here. So it has an equivalent description. Instead of working with, instead of being on the circle, I could have been on an interval. Call this point P, call this interval I, and I could have created objects. So given the data of a conformal net, I can embed this interval onto a circle and find what is this what is an abstract algebra associated to this interval. So objects are rho from the algebra assigned to this interval, endomorphisms of that algebra such that there exists J. Let's call this positive boundary of I. Positive boundary of I is in J. And rho restricted to A of J equals identity on A of J. So I can consider this category of endomorphisms of the algebra, which are trivial somewhere away from this point P. So they do something non-trivial near point P, but then there exists some interval J where they are identity. And I can give morphisms of this category, which I'll just call left localized intertwiners. So from row 1 to row 2, there is a map A, which basically is A belongs to some algebra which is localized near this point P. So the element comes from somewhere here and it's an intertwiner. So A rho 1 x equals rho 2 x A for all x in A of I. This is again a category people consider if I don't localize it. In general, just endomorphisms form this category with intertwiners. Now it turns out that these two categories are equivalent. If I just take this circle S to be I union I bar, then I can give you an equivalence between these categories. And obviously, it does not depend on this interval or the circle. There is equivalence of categories everywhere. So I'm just going to start calling this category the solitonic representations. So now we have sol of A. Now, a theorem that we were able to prove. So this category of solitonic representations has nice properties, but what was crucial to my work is that I don't assume anything about the net being rational or finite index, and I also don't assume something called strong additivity, which fails in some of the examples you would want to consider in life. So, theorem
What are those examples for curiosity?
of strong, so rationality is Virasoro at central charge greater than 1, for example. And strong additivity, I think, also fails for some nice from that.
Same.
Yeah. So theorem sol A.
But it fails for the stress tensor net, but not for the theory itself. No, it's not a bad property for the quantum field theory. No.
When I mean it fails, I mean it. There's a definition that of finite index for a conformal net, and that property fails for that Virasoro net if you write it for central charge equals 1, greater than 1.
Irrational, you don't have a nice rational extension.
I agree, but what I'm saying is that whether it's a bad property for two-dimensional conformal field theories or not, that's the question. And I don't think that shows it is not clear, because if there is an
Depends what you mean by two-dimensional conformal field theory, I think.
so we can discuss later.
Yeah, of course. I don't think it is. It's a bad thing that it fails because I'm able to show that it was not needed. So
Can I just this S you write S is equal to I.
S is equal to I union I bar, which is glued over the boundary of I.
Is S.
S was the circle that I had defined.
Circle, now you call S. No, okay.
Yeah.
No, it's 1. Okay.
So-
Okay.
I stopped writing S because I can show that I can change the circle and it doesn't matter. So sol is a bicomitant category, which was, so I had to show all these properties that it behaves like a categorified one-Neumann algebra. But the better part of the theorem is that the Drinfeld center of sol is rep for all conformal nets.
Rep is now the DHR representation.
Rep is the DHR representation. So both of these descriptions have a representation. So these are solitonic representations, but I can take DHR representation. So sol, I can just say has actions of all intervals and remove this property here. And in this case, I can say endomorphisms of the algebra such that it is trivial on both ends. And it only does something non-trivial in between, instead of doing something non-trivial localized, left localized. So the theorem is that the Drinfeld center of sol is rep for all conformal nets. So no rationality, no strong additivity assumed.
Shows that you can associate that to a point.
Yes, that is what I'm going to say. Okay, So maybe, so what I'm going to now say is that I can associate this category. So assume I have a point which comes with a little collar. I can associate the category sol A to this point because I can use this collar to embed it in a circle and construct this category, and the collar genuinely did not matter, which says that this is a good thing functorially to do. And now you can ask me, well, what about if I want to do gluing? So I have some interval I1, I2, or you can ask me what if I want to do fancier gluing? I have these arcs with P1, P2. Can I glue these things in any meaningful way? So
So this is on purpose asymmetric, right? So only one of them has a. So only on the left you have.
I can show that left localized and right localized are equivalent categories, and they're both equivalent to sol. Okay, so since I had told you that this is behaving like a von Neumann algebra but categorified, the gluing construction will behave like categorified Con's fusion. So, which I can do, but I don't have the time to tell you how it works, but I can at least write again theorem. So I'll associate a category Ti1 mod to the first interval I1. I will associate the category. So I1 and I2 don't really need to be intervals. They can be arbitrary one manifolds, but for now I'm just writing this as intervals. And this category will admit actions of the left and right boundaries of these categories. So I can fuse them over sol, let's say, P of A. So
And mod stands.
mod stands for modules. So this is the category of A1 modules. And I can easily tell you how this action works. So this was some interval I, and this was the point P. The solitons were the endomorphisms of the algebra that were trivial away from the point. So I can extend that all the way to the interval and then just compose. And that is how this action works. So this is the endomorphism of this algebra, but sort of a nice enough endomorphism, and that's how I get these actions on both sides. And then I can show that this is canonically I1 union I2 when glued over P. Again, this is a slightly non-trivial process, which you would expect, just like Con's fusion was slightly non-trivial. So we define this exactly analogous to Con's fusion. And now if I do this to this bent arc, what I get, so I told you in the beginning of my talk that if I recover the right thing at the level of the circle, I am not doing something stupid. So let me just write one last thing at the level of the circle.
I ask on the left-hand side, do you really mean A of I1, I2?
Mod.
Mod, okay.
You also have to believe me that I can use the data of a conformal net to actually get this algebra for an arbitrary one manifold. But yeah, that's a construction that can be done. Okay, so when I do this gluing now, it turns out what I get is the Drinfeld center of sol A, but it's absorbing subcategory. And that is just by the nature of how this process is defined, but not everything is broken. So this is a braided category, which is an ideal of that. But in the rational case, case, the monoidal unit uh, unit belongs to so this is equal to rep A absorbing. So monoidal unit belongs to rep A absorbing. That's my time. Therefore, rep A and rep A absorbing are equivalent, and this is shown by the work of great people in the audience, as this is an MTC. So I did recover an MTC in the rational case, and it was already expected that if I were not rational, there is no reason for this category to be a modular tensor category. But it is still recovering what we knew from the literature. So that is a good thing. So now some things that I don't know are, for example, how much of the central charge of the theory does this category Sol remember? So we already know that rep A in the rational case remembers central charge mod 8. The conformal net remembers all of the central charge, but we don't know how to recover the central charge from Sol, which is something I am trying to do right now. But yeah, thanks for listening. Thank you.